Looks like we're finally going to get to that eigenvalue today. Let's see. So we were, and so we were actually just going to FOIL multiply these operators together. And when you do that, well, we get this to start with. Okay. What can we do? We can, I take that, pull it up front. Then what you'll notice is I end up with Lx Ly minus Ly Lx, which is our commutator here. Okay. Well, we've solved for those. And then we'll take account of, so where was it? Surely I wrote it down somewhere. Here. We'll remember this thing here. So I know that. Okay. So then this becomes L squared, LZ squared, plus I squared, H bar LZ. And then we can make one more adjustment. That's because I squared is just -1. Okay. Now we're ready to start thinking about, so the last step is, this is something you'll understand better in quantum chemistry, but we have these things called eigenvalue functions. So an eigenvalue equation is when you perform, so like a wave function psi, when you perform an operation on this function, you get the exact same function back multiplied by its eigenvalue. Okay. So we're going to use the generalized eigenstate. It's defined by lambda, the quantum number m sub L. Lambda is your eigenvalue. And that's, and of course, these are going to be descriptive quantum numbers. The step operators, as we said, will step the angular momentum eigenstate up and down in the various levels. And so that means, so that we need to set up our eigenvalue equation. We're going to take the L squared operator. This is going to generate some function so you notice we get the state back, but it's now multiplied by an eigenvalue. Now, the highest achievable quantum state is where our quantum number m sub l going to equal our angular momentum L. Okay, and the way the step operators work, if you try to step beyond the maximum state, you get 0. And this would be the same for the step, the downward step operator if you had the lowest state. So if you had the ground state, you try to step it down, you get a 0.
Okay.
All right, let's see here. Okay, so now we're going to take our operators. And we're going to use this highest quantum state. And then we just solve for this. So we have L squared and you'll find out for angular momentum, like even beyond here, your m sub L quantum number is going to be a projection of your angular momentum along the z-axis. And that's what a lot of this math is telling us. Okay, now this all equals 0. There's a reason for that. So you remember you use the step operators in order. Okay, so let's say I have, so we have this here, okay? So the first thing I'm going to do is that operation there, okay? That's going to leave me using that step operator on a state of 0, which equals 0. Okay. So then let's use this side of the equation. That's going to give me L squared Nope, that's supposed to have a square on the LZ. All right. So we get here. So then we need to start giving definitions of, and again, you can solve this in more detail when you get further into the quantum mechanics, but what happens when LZ acts on the standard quantum state? Okay. We're just going to use the generalized quantum state. This is going to generate an eigenvalue of m sub L h bar, and you get the original state back. So again, this is Dirac notation. Another way to write these would be like if you were looking at the Schrodinger equation, you could just call this some wave state psi in terms of lambda and m sub L. So same kind of idea. We're just using the Dirac notation here. So that means I have LZ acting on no, lambda sub L. That is going to give me L H bar. Then what about LZ squared? That's going to be LZ. LZ. Okay, and so of course then again these work in order. So your first LZ times the working on the quantum state, and it's going to end up giving you. So you still have your next LZ. That first one is going to pull out an L H bar. You get the state back. Now we can commute these, because those are just constants now. And this is going to leave us with L H bar times L H bar. All right. So we're going to go back to this value here, or that function there, okay? And we're going to plug in our new values. So now we're going to have our L squared. Okay, so going to be L squared H bar squared. And now I'm going to pull, let's see, I'm going to have L squared plus L H bar squared lambda L. I factor out the angular momentum. And so this tells us that that function we were looking for so now we can pull this out and say that our angular momentum.
Why no H bar squared?
Hmm?
Why is there no H bar squared?
Where is it? Here.
Oh, okay. Okay.
So we so now we have our value of L, we have our produced eigenvalue, and so it's like they're both, and then you have the wave state. So it's like, all right, let's drop the wave state out and just look at what this angular momentum squared equals your eigenvalue And so now your total angular momentum of your system and so what you find is this eigenvalue that's a universal constant. Now, and here's the thing, there's a very few things we didn't do, but you'll be able to do them later because you've seen this whole process. Now that you have the whole thing, it's something worth reviewing because quantum mechanical derivations, you just have to kind of get the hang of them. But what you've done here is you've started from scratch and you've been able to find this universal constant. And no matter how many different ways you work on this, you're going to keep finding this over and over and over again. All right. Oh, still had too much space. All right, well, you go to my 73. Okay, so when we're inside, okay, so a couple of things, and so there you see, you have a couple of these. So your angular momentum could either be that square root of like your lowercase l is going to be for an individual electron. Here you have the angular momentum of an entire orbital, which is going to be you can bring together your angular momentums. Your capital L's are basically the totals of your electrons. Your m sub l values are going to be the sum of all of your individual m sub l's, which are individual orbitals. You kind of remember how your quantum numbers work. And then if you look here, your capital L 0, 1, 2, 3, 4, so on are going to align with so we're going to start talking about these things called term symbols. And they're going to align with S, P, D, F, G. Okay. Now, as you become more advanced in what's called understanding microstates and term symbols, these are another tool you can use to analyze and predict spectroscopic absorptions, because these tell you about the angular momentum and spin states inside of an atom, and that plays into all of the absorptions. Okay, so a few more quantum numbers. You know that your spin, the spin of an electron, it's a fermion, so it has a spin 1/2. So your m sub s can be a plus 1/2, minus 1/2. We usually denote that as spin up, spin down. Let's see. Your total spin is going to be the sum of all your individual spins. Your m sub s will be the sum of all of your individual m sub s's. And this is a little more abstract, these term symbols, so we'll just try to work through them. More than anything, just working through the microstate tables gives you a better idea of how all these numbers work. Okay, now the Pauli exclusion principle ends up playing a big role in this. Like, why can I have this term symbol and not that term symbol? Well, it's because, like, well, for example, one of the things you need to remember is because these are spin 1/2 particles, all of our wave functions have to be anti-symmetric. So it's like if I have a term symbol that multiplies together, say, for example, a symmetric spin part and a symmetric orbital part, I get a symmetric wave function. Well, I can't have that when I have two electrons in the same subshell. Okay. Even if you say, oh, well, they're in different orbitals. Yeah, well, your subshell is still going to be a singular wave function. You need that anti-symmetry principle. Now, let's say I have an electron in this p subshell, an electron in a completely different p subshell. Well, those two can be symmetric with each other because they're not violating the Pauli exclusion principle at that point. And this here if there's parts of it, you're like, I just don't know what that means. That's fine at this level.
Yeah.
It takes a very, like, you pretty much have to dedicate yourself to quantum chemistry to really become a master of like this stuff.
Sure.
And it's a lifetime of work. Also, remember with your microstate tables can only include unique microstates, so you can't have energetic. So they can't be technically the same thing. Okay, so it's like if I have, let's say I have an NS orbital, okay, and I have that electron configuration. I can't have that electron because those are technically the same thing. Okay, so unique microstates only. Okay, so the microstates are like, what are all the different possible combinations that you can put together here? Okay, so let's say we have a species that has NS2. Okay, well, let's take a look here. So for S, no, not one. L, your quantum number L is 0. Your values of M sub L, so are only going to be 0. Because remember, M sub L is minus L to plus L as possible values. Another thing to keep in mind, and this works for 2 electron systems, it becomes more complex beyond that, but your value of L is going to be L1 plus L2. So these are all your possible values of L, L1 plus L2 minus 1, so on and so forth, until you end up at L1 minus L2. Okay, so my M sub S is going to be 0, because if I sum together all my M sub L's, I only have 0. Well, my M sub L will equal 0. But the thing to ask yourself is, what are all the unique ways that these electrons compare with each other? Okay, well, I have my NS orbital. Okay, well, the only possible combination I can have is that one. Okay, so the way this looks in what's called a microstate table, let's see. I have M sub S there. And we said M sub S is going to have only a value of 0.
So this was a micro table?
Microstate table.
Microstates.
And then on the side here, I have M sub L. Your book does it a little bit different, but you'll be able to line this up with what your book does. Okay, and we said that it's also only going to have values of 0, because again, look at the look at this pairing here. My M sub S. So I have an electron over 1/2. Then I add the minus 1/2. My M sub S can only be 0. Okay, so technically supposed to try to make a little table out of this. So The only possible state that I have here, and now I get this from another source, but I kind of like the notation. So we have a combination 0 plus, 0 minus. Okay, so the 0 there is an orbital m sub l equals 0. And then your superscripts there, like that one, is your minus 1/2 spin. So you can think of those pluses and minuses as spin up, spin down. And so this is your only possible microstate here. So then what is the value of L? L equals 0, because if you look here, L1 equals 0, L2 equals 0. And so 0 plus 0 gives L of 0. Then your spin is also going to equal 0, because if you look at that, you're again, you have spin up, spin down. So your total spin is going to equal 0. And then you say, well, what kind of term symbol can this go with? All right, well, let's see here. So we look here at our term symbols. So this is your first type, but there's a more complete one. But this will work for now. So you have 2s plus 1, and then L is going to be your term symbol. Well, we found out that L is 0. So if I take, okay, 2s plus 1, I have my L there, L equals 0. So, and then what is 2s plus 1? So 2 times 0 plus 1, that's 1. And so we end up with a 1s for our term symbol. This 1 is a singlet spin state.
What does that mean?
So most of the time it means that all of your electrons are paired, all of your spins are canceling each other out. You end up with you pretty much have a total spin of 0 across your molecule. It becomes more complex as you go on, like an open shell singlet, but that's where it's like I can have my spin state still equal 0, but the electrons they're technically in the same orbital, but energetically they're in their own unique positions. But that takes a lot more quantum mechanics.
Okay.
But these spin states, so this is like your common, a lot of your common molecules are singlets. So again, your electrons are paired, their spins are canceling each other out. And this is basically your lowest angular momentum state. So it's going to absorb photons in its own unique way. This is kind of like you would say your ground state. Okay, so then here, again, you can start to set up your term symbols using this. Your 2s plus 1, again, it's called the multiplicity of the atom. A quick way to kind of look at it is, let's see, if you have one unpaired electron, that would be a doublet. 2 unpaired electrons, because the easiest way to think of 2 unpaired electrons is they're both going the same direction. Now, in this case, you'd have 1/2, 1/2. Add those together, you get 1, your 2s plus 1. So that's going to be a triplet state. They don't necessarily, just kind of think of it like this for now. They don't necessarily have to be spinning the same way just to get a triplet, but this is the easiest way to start to think about it.
Okay.
So here you have singlet, doublet, triplet. But let's make it a little bit harder. Let's say we have this. So instead of both of the electrons in the same subshell, They're now in different S subshells, okay? So then so what are all the possible microstates that we can have here? Well, we know for S, your L quantum number is 0. The only possible M sub L is 0. However, this is more of an open shell system where an open shell system, electrons have the ability to place themselves in different areas. A closed shell system is your electrons go here, that's where they go. So like you're locked into that electron pairing or the Aufbau principle or Hund's rule or something like that. You're locked into these specific positions for electrons. That's closed shell. And so we say, okay, so what are all the possible microstates that I can think of? So again, we want to remember L, L1 plus L2. Okay. All right, so I know, let's do electron 1, electron 2. Since they're not in the same subshell, this time I can have that configuration. Then I can have this configuration. I can have this one. And I can have this one. So we're going to get plus 1/2, 1/2, 1/2, minus 1/2. Okay. And because there are different subshells, these are all unique. Okay, so here your MS is going to be 1/2 plus 1/2 equals 1. Your L is going to equal 0. Your spin is going to equal 1. Okay, so at this level, M sub S is going to be 1/2 minus 1/2, so that's 0. Spin 0. Hang on, let me see here. Well, I'm going to correct this, and I'll try to explain why. This is more abstract. We're going to say, well, we're going to say this is going to be spin 1. Okay, I'll explain why here in a second. Let's see, minus 1/2, minus 1/2. So here, we're going to get a -1, L equals 0, S equals 1. So again, your spin is not, you can't have a negative spin. Okay, you can have a 0 spin. But you notice here that we have 3 spins of 1 and 1 spin of 0. With 3 of our S's equal 1. So you know that a 2S plus 1, that's going to be a triplet state. Well, the fact that we have a triplet state, you have to have 3 microstates available for that triplet state. Even though it looks like in one of the, so that second from the bottom, that looks like it should be a spin of 0. You have those 2 spins right in the center, you have those 2 microstates right in the center. One of them has to be in the under the triplet term symbol. The last one is under the singlet term symbol, because a singlet takes a singular spin state. Okay, so our M sub s's, we're going to go from the range is -1, 0, +1. L equals 0. You can, your L for your system is going to be the maximum value of M sub L. And then you're going to have 0 for your M sub L. And then what are our microstates? So for our -1, let's see, for our -1, we're going to have 0 minus, 0 minus. In the center, oops. Okay, and then over here, we have 0 plus 0 plus. So those are our microstates. Again, that 0 is your M sub L equals 0 level. So this kind of sets in motion something you see where your M sub S values are also going to range from S -1, S-2 to -S. Now, S itself, so when you're looking at the spin of your system, you're thinking about your multiplicity, S can't take a negative value, but on your microstate table, it can, okay? And in the center, what you end up with is you end up with two states that provide two completely separate wave states. So your first one, remember our linear combinations. Then you're also going to have and so what this means is this one is the one that goes into the triplet regime. And that one is your singlet. Let's see. All right, so let's look at our states here. We have 2s plus 1. There's our generalized term symbol. Well, for all of them, L equals 0, which equals S. Okay, but we have S equals 1, which gives 2 times 1 plus 1 equals 3. We also have an S equals 0 state. 2 times 0 plus 1 equals 1. So the two possible angular momentum states that we have here are a triplet S and a singlet S. And so your triplet S again has to have 3 total states. What is the equation? tells you how many microstates each one gets. So to know how many microstates each term symbol gets, so you have 2L plus 1, 2 times 2S plus 1. That tells you how many of your states each one gets. Now, the reason this is more abstract is you look here in the center, you can't really look at this and say, well, that one is the singlet and that one's the triplet. It's just one of those goes to the triplet because the triplet has to have three microstates allotted to it. Sure. I'm showing you the process of this right now. As you go along and you get better at this, it starts to make more sense. But this all of this plays into something you would see experimentally in a spectroscopy lab. So it's good to know how it, like, basically the math and how it works, so that later on you can start to really look at the data and understand why it is that way. So let's look at a P2 species here. Now, I told you about like symmetric versus anti-symmetric. So again, we're back to 2 electrons in the same subshell. So we have to have an anti-symmetric wave function this time due to the Pauli exclusion principle. So up here with this NS1, N prime S1, we could have a symmetric wave function because these 2 electrons are in 2 completely different subshells. They're each one of those is would technically be an anti-symmetric shell, but due to the fact that there's only 1 electron in there, it's just kind of automatically there because of the spin 1/2. But when they're both in the same subshell, you have to guarantee that the wave function is anti-symmetric. Okay, so what do we have here? For P, L equals 1, our values of M sub L are going to be +1, 0, and -1. Let's see, we want to remember that our M sub L will be the sum of our M sub L's. Okay, so what are all the different ways that we could have these? So let's think of our P orbitals. So you remember we have 3 of these. We have a +1, a 0, and a -1. Those are our M sub L's. Now, where could the electrons be? Okay. They could both be there. They could be there. They could be like this. Well, we could have a downspin there. So you're getting the point. There's a bunch of different combinations of these electrons in these 3 orbitals. Okay. So we're going to start with, let's say they're both in the M sub L equals 1. Okay. So that's going to give us a capital M sub L of a +2. And there's only one possible state for this. If they're both going to be in the same orbital, they have to be anti-spin. Your M sub S is going to be 1/2 minus 1/2 equals 0. And your state is going to be 1 plus, 1 minus. Does that make sense?
Yeah.
Because they're both in the M sub L equals 1. You have a plus and a minus. There's no other states we could have for that. Okay, so that was that one. Now, let's look at our states for, now we're going to have, where we're involving +1 and 0. Okay, so that means your M sub L is going to be a +1. Now, what are all the possible states for this one? Okay, so we could do spin up, spin up. Okay, we could do spin down, spin down. Let's see, we could do. And so I'm going to start marking these as +1 and 0, +1 and 0, to let you know which M sub L it is. So I could have an up, down. And I could have a down, up. Okay. Let's see. And again, this was for M sub L equals 1 and M sub L equals 0. Okay, so then what are these? Let's look at actual microstates. Okay, so this one here, that's going to be a 1 plus, and that one's a 0 plus. This one is a 1 minus, that one's a 0 minus. This is a 1 plus, this is a 0 minus, 1 minus, and a 0 plus. So there's our microstates for that one. Okay, we will pick this up on Wednesday because we've run out of time.
Okay.
We'll do a few more of these trying to get this in your head a little bit, but this is one of those topics that if at first you're like, this is really abstract.
Yeah, no, I get what you said. This doesn't make any